All right, so today we're going to learn about just one more way to calculate delta H. And so I'm going to use the question from 2012, number 3, to help us understand it. And the key here, I'm going to answer question B. I'm going to show you how to use it. And the one thing to look at is what numbers do they give you. And they give you bond enthalpy or bond energy values. All that is saying is how much energy does it take to break these different types of bonds. And so what we're asked to do here, so you see in B, you're asked to find delta H. So this is the formula that you need to know. Delta H equals bonds broken minus bonds formed. So that's our formula. Notice these are all positive numbers. They're all positive because that's endothermic. And remember we talked, if we want to break things apart, you have to put energy in. If you form new attractions, it's exothermic, it releases energy, and that's why you see you're subtracting the bonds formed. This is going to be a little different. We are going to break all the reactant bonds. So we're going to break all of those apart in order to make or form all of my product bonds. So the other formulas we looked at have been products minus reactants. This one's a little different. It's reactants minus products. And this is what we do when you're given bond energy values. Now, in order to know what bonds are present, you got to draw the Lewis structure. And so here we see they give us the Lewis structure. So it's just a matter of us counting up bonds. Whereas in practice questions you'll look at later today, some of them, they only give you the chemical reaction. They don't give you the Lewis structure, so you have to draw the Lewis structure first. And so when we look at this bonds broken minus bonds formed, all we have to do is refer back to the Lewis structure. Now, for me, I break all the bonds, I form all the bonds. That way I don't have to worry about missing anything. And so when I look at bonds broken, I want to figure out, well, what type of bonds do I need to break? Well, one of them I need to break is a carbon-hydrogen single bond, and I see that right here. But I need to break 1, 2, 3, 4, 5 of those, so I've got to multiply this by 5. I also need to break a bond between nitrogen and hydrogen, a single bond, and I need to break 1, 2 of those, so I'll put a 2 here. And then lastly, I need to break this carbon-nitrogen single bond. And I only have one of those. And so what you've noticed, I mark out the bonds just so I make sure I count for all of them. So what you see here is I've counted for all of the bonds that we have broken. And so now I'm going to subtract the bonds formed. And so what bonds am I forming? Well, I need to form a carbon-hydrogen single bond. And I need to form 1, 2, 3, 4 of those. I need to form a carbon-carbon double bond, and only one of those. And then I need to form a nitrogen-hydrogen single bond, but I've got 1, 2, 3 of those. And so again, all I do is I go through and I'm just looking at what bonds do I need to break, what bonds do I need to form, and I just list them out. And now from here, it's just a matter of taking the numbers you're given in the table and plugging them in. So 5 times the carbon-hydrogen single bond, so that would be 413, plus 2 times nitrogen-hydrogen, which is 391, plus only 1 carbon-nitrogen, which is 293, minus 4, so carbon-hydrogen is 413, carbon-carbon double bond is 614, and nitrogen-hydrogen single bond is 391. And so now that we have those numbers, all we have to do is plug this into the calculator, and we can then solve for what delta H is. So I'm going to separate these out just to talk about a couple things. And so we can get that delta H equals (483 kilojoules per mole). And so a couple things to talk about when I look at this. And so here, when we look at C, and some people ask questions on this in previous questions, predict whether the temperature of the contents will increase, decrease, or remain the same, and justify your prediction. Remember, the contents is going, when you measure the temperature of the contents, usually you're measuring the temperature of the surroundings. And so I would say for here, what would happen, I would say that the temperature of the contents would go up. Why would the temperature, I would say the temperature of the contents goes down. This is an endothermic process, so in order for this reaction to occur, it has to absorb energy. Where is it going to get energy from? From the contents. The energy is going to go from the surroundings, the contents, into the reaction, therefore making the temperature of the contents go down. And so when I look, and another question looked at this, when I look at explaining endothermic versus exothermic, some people were a little confused here. And so when we look at explaining endothermic versus exothermic, we can use this formula to help us explain. So when I look here, and so I'm going to kind of move this up. We don't really need this anymore. But when I look at explaining endothermic versus exothermic, something that I use this formula to help me explain it. All right, let's see. So we know that delta H is a positive value if it's endothermic, right? So, and we know that delta H is a negative value if it's exothermic. And so when we look at the formula, in order for it to be a positive value, that means that this is going to be a bigger amount. Or you would think more energy is needed to break reactants apart. So when we look at this and we're explaining, if this is a positive number, that means that you had to put more energy in to break the reactions apart than the energy that you got back out when the new bonds in the product formed. So what does exothermic mean? Exothermic means that this value is a bigger number, right? So if this is bigger, it'd be negative. And so what would that mean? That would mean more energy is released when the new product bonds formed than was required to break reactant bonds. So when we look at endothermic or exothermic, why is a process endothermic or exothermic? What we can look at is we can look at the amount of energy it takes to break the reactants apart and compare that to the amount of energy that we get back when the products are formed. And remembering that if we want to break bonds or attractions, we got to put energy in. When we make new bonds or attractions, we get energy back out. And so that's why you see this being minus the bonds formed. So we can use this question, 2012 number 3, 1, to help you understand, well, how do I answer the question when I'm given, remember what we're given here. We were given bond energy values. So whenever we are given bond energy values, we got to draw the Lewis structure if we don't have it to know the types of bonds that are present. Then from there, we're doing bonds broken minus bonds formed. And then from there, we can plug our values in and calculate. And then again, this may just help some of you understand more so explaining endothermic and exothermic processes.